Artistic deep learning methods like style transfer allow us to create beautiful artwork from everyday images. What's up y'all, it's Fuego, and if you saw my first video on style transfer, you saw how we stylized a few selfies to match some pieces of artwork by Jean-Michel Basquiat. To summarize, the initial style transfer method takes a style image and a content image, and defines a loss that measures how well the style matches the original style image and how well the content is preserved in the content image. Then we optimize those losses, with the object of optimization being the actual content image so that we stylize that content image. Over time, the style of our content image looks more and more like our style image. Now, there are two issues with this method. The first is that the data had to be manipulated to match the general style of the artwork. For example, I had to change the saturation of my images to get my face to match the faces on the Basquiats. The second thing is that this method took a pretty long time to train. It takes about 5 to 10 minutes to stylize a single image, so imagine if you had a 5-minute video at 24 frames per second, it would take you about a month to stylize an entire video. This is obviously unrealistic for real-time applications. Now, since the conception of this idea, people have found ways to use classic computer vision methods to speed up this evaluation in real time. Specifically, one paper on fast neural style transfer trains an encoder-decoder model to style images in real time. But what is an encoder-decoder model? To understand the encoder-decoder model, we can think of the classic computer vision model. When we design the structure of our machine learning models, we have to make sure that our model takes in whatever size input our desired input is and outputs whatever our desired output is. For the standard classification model, this might be some probabilities on each class. For a depth estimation model, this might be something like a single channel image. Well, the encoder-decoder model is basically the general model that can do all of these things. We encode our image into a low-dimensional feature vector and then decode that feature vector into whatever our desired output be, whether that be an image, probabilities on classes, or whatever that is. The nice thing about this model is that you can train one encoder and multiple different decoders for several different tasks. This can be used for any machine learning algorithm that wants to output a value at every single pixel in an image, such as depth estimation or style transfer. To use this for style transfer, we can actually use the same style and content losses that we used in the original method, but while we train, we take a whole bunch of images and evaluate the style and content loss for each image as compared to our desired style. Similar to the original method, the style loss makes sure that the style matches our desired style image and the content is preserved from every single image. This is great, but with this method, we end up creating a new model for each style we have. If we wanted to do this with arbitrary styles, this wouldn't be efficient. Well, another method actually defines an encoder for the style image as well, and then combines both the image and style features during decoding to produce a stylized image. There's actually code on GitHub for this provided by Google's Magenta project with a quick little tutorial on setting it up and training a model. The tutorial is also really easy to follow along with if you're a beginner. I also have a Colab notebook that follows this repository closely, and the notebook provides functionality to stylize a source image with a set of styles, in this case all my Basquiat styles. Rather than taking 10 minutes per frame, it takes about 10 minutes per video, which is much faster than the original style transfer method. However, this is for a 30-second video. If we want to speed this up to real time, we have to talk about deployment. If you're familiar with machine learning, you're probably familiar with GPU and TPU, which are accelerated processors made specifically for graphics and machine learning. GPUs accelerate deep learning by providing fast ways to multiply matrices, but they can also be used for general graphics processing on your desktop or laptop display. TPUs also accelerate these calculations, but they have much more advanced features specifically for doing deep learning, so it's even faster than the GPU. However, speed's definitely not cheap, and the average consumer doesn't want to buy a GPU or TPU just to run your machine learning model in real time. So to support the average consumer, there are a couple deep learning frameworks for real-time evaluation. The first is called ONNX, and ONNX allows you to compile trained models for inference that run much faster than models designed for optimization. There's also a package that allows you to run these models in the web browser, which would allow you to deploy virtually any machine learning model on the internet. The next is TensorRT, which is another compiled model runtime environment that allows you to actually run extremely fast on GPU, and it's often the preferred choice when deploying to popular embedded GPU systems such as the NVIDIA TX2, which is a very popular board for embedded systems projects. TensorFlow.js is also a really great package for deploying machine learning models on the internet. TensorFlow.js allows you to specifically export TensorFlow models for use in the browser on any computer in the world. And I also love TensorFlow.js because of all of the great web examples they provide, like this fun one that turns your webcam into a Pac-Man controller. These examples provide you basically anything you'd want to know for deploying your TensorFlow models on the internet. Comment down below if you're interested in any specific example of deploying machine learning models on the internet. That's it for this video, and I'll see you on the next one. Later!